All right, so now let's go to the second section of the chapter. We are going to construct the Lebesgue integral. This is something just to show you where these tools come from. So here we've got some definitions. I'm not asking you to know these definitions, I just want to show you that it exists. It has some very nicely grounded theoretical setting. We can define measure space, measurable function. What is these are some definitions that you can take some time to read. We want to be able to, for the things, the sets that we are going to measure, we want to have a few things. We're going to define the measure. It's going to be usually denoted with a mu. And we want that if you're doing the empty set, you're measuring the empty set, of course, it's going to be 0. And the important thing is that for countable collections, if you've got a collection of sets that you can count, you have that the measure of the union is the sum of the measures. So actually, this is some correct setting to work with exactly the same way you've been doing for many years now, to work with intervals. All right. So the measure of an interval is simply its size. So measure of interval AB is going to be B minus A if B is bigger than A. And the good thing is that it satisfies those properties. But the good thing is that this can be extended to non-standard measures. And in particular, these are some big applications in statistics or in quantum mechanics, because you are in other areas of physics, because then you can give more weight to some parts of the universe. That's the broad idea. But for us, we're just I'm just asking you to remember two things. The measure of an interval is the size of the interval, so as natural as intuitive as it is. And the second thing is that if you measure isolated points, if you measure a set that contains only isolated points, it's going to be 0. And even more, if you do union and even infinite union of isolated points, it's going to be a set of 0 measure. These are what are going to be called negligible. Negligible sets are the sets that have 0 measure. That's the definition. Okay, so again, this whole paragraph on measure, you don't need to know. It's just for your culture if you want to have a look at how we can define some very abstract ideas like this. So from this negligibility idea, we can derive the almost everywhere concept. And this is a very nice one because, well, you know that in math we used to have 0, 1. It was very either things are equal or not equal. But here we can introduce some subtleties, some shades to this. We can define the almost everywhere concept, and in probability it's will be interpreted as almost surely. It means that things are almost sure when they have a probability of 1. And for us, we're going to say almost everywhere if something is happening everywhere except on sets of null measure, meaning for us, for instance, that we can say that two functions, so you will sometimes see measurable functions. For us, all functions are measurable. I have never met a non-measurable function, but well, these are the kind of things that you will see if you look at some math literature everywhere. So given two functions, we can say that f is equal to g, AE, meaning almost everywhere. What does it mean? It means that the measure of the set that contains the points x where f is not equal to g is equal to 0, right? So what does it mean to have equality almost everywhere? It means that they differ, they are equal everywhere except, maybe at some at some isolated points. Okay, so that's this very important idea here. All right. For us, we will use this idea of almost everywhere when we talk about pointwise convergence almost everywhere. So let's see what it means. So we're going to consider a sequence of functions, for instance, fn of x, so just the kind of things we've seen in an example before. So sequence of functions, you've got its functions of x, but that depend on some index n, and some parameter n, and that makes a sequence. And we can say that this sequence converges to some specific functions. So we've got pointwise convergence. Pointwise convergence, it means that, well, here you've got the epsilon definition, but actually pointwise convergence, it just means that fn of x tends to f of x as n tends to infinity for all x in your domain, right? That's just the usual limit. We've got uniform convergence, so it's a slightly, it implies a pointwise convergence. It's something we're not going to use. It's just that it converges at the same speed. Well, you can find a uniform speed so that the convergence happens everywhere for all x's of your domain. And what we want to talk about is pointwise convergence almost everywhere. It means that instead of having this limit for all x, we just need that it's happening almost everywhere. What does it mean? It means for all x except maybe on isolated points. Okay, and then you've got convergence measure, but really, the only thing that we will be using this year is this one, and I hope we will try to do it in a very light and intuitive way. Okay, let's see an example, right? So pointwise convergence almost everywhere. This is what we want to deal with. So convergence is almost everywhere if this limit happens for all x in R. Okay, and for all x maybe on sets of zero measure, that's all x maybe for isolated points. Okay, so let's look at this one. So we've got a function defined by outside of negative 2 pi, it's going to be equal to 0. And in between negative 2 pi and pi, it's going to be equal to cosine of x. Maybe we can have a look at that. So let's say that it's 0, that's negative 2 pi. So that's negative pi, that's 2 pi. Right, and this is for 1, cosine, well, for 0, it's just the constant 1 function. But for 1, f1 of x, that's just going to be cosine of x. So cosine of x, that's, that if I said that was 2 pi. Okay, that's the one. Sorry, that's really looking ugly, but well, you see the idea. That's 2 periods of the cosine function, right? If you make f2 of x, what's that going to be? Cosine square of x. So it's going to be a slightly harder to draw, but it's going to be something that, well, it's 1 here. The ones are going to be here, so this one is going to be here, and then it's going to be slightly smaller, something like this. The representation is not very good, but the idea is that we want to understand what it's going to do as n tends to infinity. Okay, so cosine n of x as n tends to infinity. Okay, so what is the limit function? Okay, so only for x between negative 2 pi up to 2 pi, because that's outside my sequence of functions is equal to 0. So maybe you can pause now and have some thoughts about it. Okay, so assuming you have been pausing your video, it's still time to do it if you haven't. Let's try to understand. Well, maybe let's take one value, cosine at 0. Cosine at 0, it's equal to 1. So whatever the value of n, it's equal to 1. We have the same stuff for 2 pi, for minus 2 pi, and for, well, what are the other values we can find? For, what else do we get? for pi and minus pi, we're going to have -1 to the n. For pi over 2, we're going to have 0. And what for the other ones? Well, for the other ones, for x different from those pi, 2 pi, well, k pi, and k pi over 2. All right, all these specific values, what do we have? Cosine n of x, it's going to be strictly between -1. Oh, sorry, that's supposed to be a strict inequality. That's the whole that's what's good about it. It's that this inequality is strict. So that's strictly between -1 and 1. So when n tends to infinity, that goes to 0. So as to sum up, what do we get? When n tends to infinity, fn of x tends to 0 for all x different from k pi. Right? So what is the limit? The limit function that we obtain, it's going to be 0. Sorry, I wanted to use another color. It's going to be 0 everywhere except in 0. It's going to be 1. In minus 2 pi, in plus 2 pi, and in pi and minus pi, well, the limit is undetermined. The limit doesn't happen. We don't know. It's going to be plus 1. It's going to be just oscillating between plus 1 and -1. So what's happening here? What we can't give a limit function, but a pure limit function, a pointwise limit function, but we can give the pointwise almost everywhere. Almost everywhere it's going to be equal to the 0 function. Okay, there are some isolated points where either I have no limit value, so like in -pi and plus pi, and some points where it's equal to 1, but they are just isolated points. And the measure where of the set where the function does not tend to 0 is equal to 0, because that's the measure of isolated points. So this is the AE, almost everywhere, pointwise convergence of this function, of this sequence of functions towards the 0 constant function.